Okay, so this is going to be a continuation of the lecture from last Wednesday from 11 to 12:30. This should be the lecture for Monday from 11 to 12:30 for the Kines class PTA200. We finished last time talking about the roll, spin, and glide of joints, arthrokinematic versus osteokinematic motions. So now we're going to actually talk about the muscular system just to review it. Again, like I said, the whole lesson is just a systematic review of Intro to Kines so that you guys don't forget what you learned last semester. So with your muscles, they have an origin, an insertion, and some actions, right? The origin is the most stable portion. It's closer to the trunk and or the axial skeleton. The insertion is usually going to be more distal, and it's going to provide for more mobility, usually at the distal portions of bones. Some muscles, obviously all muscles have actions where they do one motion. Some muscles are able to do a reversal of muscle action, such as the biceps and the hip flexors, where they can actually allow it to do the reverse of what it's supposed to do. So here's a biceps, right? Bringing the drink up to the person's face, where it's moving the insertion towards the origin for shoulder flexion. And then here we have a closed kinetic chain, right? Where it's actually going to move things away from the insertion. There's the good old upper traps, right? And they allow to do things like that. You can do both ways with the upper traps. Muscles are characterized by their location, their shape, their action, the number of heads or divisions of the muscles, plus also the attachment, origins, and insertions, the directions of the fibers, the size of the muscles. Pretty much everything has to go along with the way the muscles are named, right? Such as serratus anterior is named because of its shape. It's sawtooth. Sternocleidomastoid is named for all of its attachment points. Fiber arrangements. The muscles typically run in a parallel type fashion where they run almost in line with what they're doing, right? Usually the longer and the greater range of motion muscles are parallel. They have a strap-like function like the sartorius or rectus abdominis. You can have fusiform muscles like the elbow flexors where they all kind of work together to do it. Rhomboidal, where they're kind of square off, like pronator quadratus, gluteus max, or triangular like pectoralis major or your piriformis that allow for narrow, broad attachments. They can have more oblique or feather-like arrangements and attached at oblique angle. They can be unipennate, where they're just one section, like posterior tib, flexor pollicis longus, semimembranosus. They can be bipennate, where they have two type things coming off. The interossei are great examples of that, or the rectus femoris at the hip, or they could be multipennate, like the deltoid and subscapularis. So pennant muscles, this is kind of how you calculate the amount of force they can actually generate. This is an F, Y, I. This is not something I'm going to ask you specifically on your test. So it's here, but don't totally freak out about it. So here's kind of like looking at those, the different types of muscles. So functional characteristics of these muscle tissues. They have a normal resting length, right? This is the muscle at its unstimulated point, right? So your biceps typically have that normal resting length when your arm is fully extended. We have to have the irritability, where if you stimulate them, they have the ability to actually react to that stimulus. Contractibility is the ability to shorten or contract. Extensibility is the ability for it to lengthen or stretch. And then elasticity is the muscle's ability to return to that normal resting position or the resting length. If you lose elasticity, that's kind of one of the most difficult things that you can have, because at that point, the muscle is actually going to end up being shortened forever. Tension, right, is the force buildup within the muscle. There is active and passive tension. Your muscles have just a passive resting tension as it is, and that allows them to react to that stimulus as it comes in. There's tone. Slight tension present at all times allows for quick and easy action. When you're at rest or sleep, you have a lower tone than you are when you're awake. And the excursion is the total distance from max shortening to max lengthening, right? When you look at the bicep, it has a good distance it can move from its short period to its long period. So there's looking at the contracted position. There's our excursion, the total distance it moved. There's our normal resting. And then obviously it has a stretched position as well. All right, so active versus passive insufficiency. This seems to catch a lot of people. Active insufficiency, the muscle cannot shorten. So active equals shortening, right? So with the biceps, that would be up into flexion, right? And shoulder flexion. Passive insufficiency, the muscle cannot be lengthened any longer. At that point, we're talking about the biceps being extended, right? So the elbow's fully extended and the shoulder goes into extension. When you're stretching a muscle for PT, you have to take into account whether it's a one or a two joint muscle. Because if it's a one joint muscle, it's fairly easy to figure out how to stretch it out. You just go to the opposite length of, or opposite direction it's going for flexion, right? When you have two joints, you may have to think about it, right? For the bicep, it's crossing over two joints and even kind of has a third joint with the radial ulnar joint with pronation and supination. So you have to actually think totally going, oh, if I want to stretch it, right, I've got to totally reverse its muscle action. So when you're thinking of stretching a muscle, think of what actions it does as a whole and then reverse all of them. As long as you reverse all of them, you go into the most elongated position for stretching. So here's looking at active insufficiency, right? Active knee flexion after hip extension, and then we have passive knee flexion. So this shows how things can shorten at that, sarcomere level and how everything can shorten up, right? But it also shows that we have a certain amount of active insufficiency here, right? Where we can contract it, but we can't contract it more. But if we pull on it, it gets a little bit shorter as well. So that goes back to that original term I said, where the muscles have more passive range of motion than active range of motion. We tend to not fully contract as far as we possibly can. So here's passive insufficiency, right? Bending down to touch your toes. More range of motion when stretching over one muscle group. Stretching over two muscles allow for less range of motion. So at this point, we've got everything kind of lengthened out as much as they can. But if you come up to that person, put your hands on their upper back and push down, they probably still can get 1 or 2 more inches and reach towards the ground. But that's where they're at their full passive insufficiency of themselves. So here we have the hamstring stretch over the hip and the knee joint. The hamstrings are contracted in hip extension. The hamstrings are stretched in knee extension. So when you look at all of this, part of the hamstrings being shortened, part of the hamstrings are being lengthened depending upon what you're doing. If we wanted to fully lengthen the hamstrings, we'd want to do hip flexion along with knee extension to fully lengthen them. So types of contractions, right? We have isometric versus isotonic are your primary contractions you're going to deal with. Isometric in the Greek words means same length, or isotonic means with same contraction or with contraction, right? Isometric, we like to think of there being no movement. That's not 100% accurate. In the term of no movement, it means that they're like your joints aren't particularly moving. The muscles themselves are still moving, but the actual joint itself is not moving. Isotonic, on the other hand, you typically are going to have two different types. You're going to have a concentric, where the muscle's lengthening or shortening, or eccentric, where the muscle's lengthening, right? And just remember that primarily we exist in an eccentric world, meaning that for the most part, we do a lot of eccentric loading of our muscles. So when you're working with patients in physical therapy, you need to make sure that you are doing eccentric loading on those muscles because you can't avoid it in life. And isokinetic, typically we're going to do with the machine, which is fixed speed and variable resistance, right? So the biceps. When the biceps contract up, right, they're doing a concentric contraction when they're lifting the curl. When they actually go back down, they are doing an eccentric contraction, right? Because the joint is still changing, the angles are changing, the muscle length is lengthening. Eccentric loading your muscles really works them hard. If you want a challenge of it, try going to your gym and doing an all eccentric day where you work on slowing the muscles down after they come out of their fully contracted position. You'll be pretty sore the next day and usually have pretty bad DOMs. Here's looking at the quadriceps doing the same thing. Here's an isokinetic machine, right? A lot of times you'll see this in work hardening places where the clinic is trying to get the patient back to work in order to, get them more prepared for returning to work and stuff like that. It's very rare you're going to see it in every clinic, but you'll see it in a lot of clinics. So agonist versus antagonist. If you get nothing else out of this lecture, this is one of the important things you have to get. I mean, the contractions are important too, you know, your eccentric versus concentric, but agonist and antagonist for some reason is a really difficult concept for students. The agonist is the muscle that is causing motion. It is the prime mover. The antagonist is the muscle that is actually causing resistance. It performs the opposite motion of the antagonist, right? So I like to think of this in terms of like books. Your agonist is your main character that's moving the plot forward, right? So if you look at something famous like Les Mis, right? Your agonist of that whole book is Jean Valjean. He's moving the full story forward. Your antagonist at that point is Javert, right? Who is the police officer searching for him across the whole time. With muscles, same idea. The agonist is the one that's moving. The antagonist is the one that's resisting the motion. A stabilizer provides support to allowing muscles. Most of our stabilizers are our core muscles. Neutralizers work to prevent unwanted motion, and then synergists work with the muscle, right? So when we're doing hip flexion, there are many muscles that work in synergy with one another to allow for that hip flexion to occur. Closed versus open kinetic chain. I hope you guys got this. It seemed like you had a really good grasp of this when I asked you guys last week about this. Closed kinetic chain, right? The distal segment is fixed and the proximal segment moves. The forces applied is not enough to overcome the resistance from the load. So when you're doing something like a sit to stand, that is a closed kinetic chain activity because the distal end is fixed. Open kinetic chain is the distal segment is free to move, right? The proximal segment is fixed. So at that point, you're sitting down in a chair and kicking your leg up. That would be an open kinetic chain activity. Force applied is enough to overcome the resistance, right? And the resistance for that kick up is going to be gravity. So here's closed kinetic chain. There's our open kinetic chain picture, right? Basic biomechanics. Oh God, no, you mean physics is coming back to haunt us? Yes, physics is coming back to haunt you. So we got to talk about Newton, right? Not the guy that developed the figs, the guy that developed kind of motion. Newton's first law was the law of inertia. An object at rest tends to stay at rest. An object in motion tends to stay in motion unless acted upon by an outside force. Our bodies are the same way, right? And then the second law, which is the law of acceleration, the amount of acceleration will depend upon the strength of the force applied to an object. The acceleration is inversely proportional to the mass, meaning the more mass you have, right, the slower your acceleration, the less mass you have, the greater your acceleration you're able to accomplish. And then, of course, there's that third law as well. For every action, there's the equal opposite reaction. That's going to come into play when we talk about reciprocal inhibition. I haven't quite got there yet, but reciprocal inhibition happens when one muscle contracts, another muscle relaxes. That would be very applicable to Newton's third law. For when there is an action, right? So when your biceps contract, your triceps relax. That's a very key thing right there of Newton's third law. Right? So force has a magnitude, direction, and a point of application. Right? We talked about this in physics. A linear force is moving on the same line. You can either go in the same line together or against. And remember that your net force then is what your total force is once you equal out those forces. So in the first case here where we have these two people, if this guy's pulling with 10 newtons of force and this person's pulling with 10 newtons of force, the total force is going to end up being 20 newtons, right? Whereas if we go down here and this guy's pulling with 5 newtons of force and this guy's pulling with 10 newtons of force, your net force eventually is going to be 5 newtons of force towards the guy with the greater pull, right? Whereas in this one here, you're going to have a total 20 newtons of force that way. Why does this come into play? A lot of times this is going to come into play when we talk about orthotics and prosthetics, because we need to look at how the forces are acting upon those. In this case, we're looking at a postural correction brace, right? We'll get into the terms of them later, but in this case, we're trying to keep the patient standing upright as much as possible and avoiding that kind of kyphotic posture. So we're going to apply force on 3 different areas, right? So in this case, we're looking at this specific one. I want to change colors. Let's go to purple. Purple sounds good. So there's going to be 5 newtons of force applied there, 5 newtons of force applied there, and probably 10 newtons of force applied here. So my net force is 0 newtons. But the goal is it's keeping that person straight up and down, right? The problem comes into play here if you don't understand forces and maybe instead give them 10 newtons of force here, 10 newtons of force here, and 10 newtons of force here. Well, then your net force is going to be 20 or 10 newtons of force that way, because 10 plus 10 equals 20 minus your 10 this way. You still have 10 going that way, and that person's going to end up with that posture like that again, and your brace does nothing, right? So you've got to be able to make sure that your forces equal out. Concurrent forces are 2 or more forces acting on a common point, right? But must push and pull in different directions. And that resultant force is what happens when you look at those 2 concurrent forces. So the resultant force here, we're looking at shoulder abduction, right? So at that point, we have that multipennant muscle being that deltoid. And the deltoid has multiple parts of it, right? So it is the anterior, the middle, and the posterior section of the deltoid. If they don't pull at the right amount of force, you can have an uneven overall abduction force. You need to make sure that they're pulling at the right forces, or you could come up weird, right? If you pull too much, you might get more flexion. You pull too little, you might get more extension. Or if you pull too much laterally, it just might overcome everything. So everything has to be equated out when the resultant forces occur. Here we have 2 people carrying a bunch of stuff, right? The force that's pulling it down at that point is going to be gravity. And then the force that's pulling up is going to be them holding it. If their force lifting those, let's just say those are mats, lifting those mats up is greater than the pull of gravity downward, they're actually going to keep lifting those mats up until they can't lift them up anymore, right? If they want to keep it equal and keep it with gravity so they can carry it across, they just have to take off gravity. And remember that gravity only ever pulls us down, right, with about 10 newtons of force per kilogram, right? So if they can overcome that, right, so if it's pulling us, let's say this is 1 kilogram, it's got 10 newtons of force, they both only have to exert 5 newtons of force in order to overcome it. Whereas if only one of them lifted these mats, that one person would have to exert 10 newtons of force. That's why multiple people doing work actually makes things easier. So with the resultant force of the gastroc heads, right? So the gastroc, one head is going to pull slightly more medial, one head's going to pull slightly more lateral, but the resultant force is going to be between them, right? So you're going to have that force that kind of comes, as long as the head's forces are pulled, it's going to come between them and allow for plantar flexion. Force couple occurs when 2 or more forces act in different directions, resulting in a turning effect. This is an excellent example of the rotation of the scapula. We'll talk a lot about that force couple of the scapula, especially when we get into the shoulder. In this case, we're going to have the upper trap pulling the outer tip of the scapula towards the ear. The serratus anterior is helping to lift it out towards almost the armpit. And the lower trap is going to actually pull the inside tip of the scapula down. All of that's going to allow rotation of the shoulder, which allows us to get full shoulder flexion. That's the important part there. If we don't have all those forces occurring, right, even if we knock out just this lower trap, well, now this tip's not being pulled downward. So this is going to have to work harder. This is going to have to work harder in order to obtain full shoulder flexion. Or we may just get stuck. We may only get partial and we're stuck where the tip only goes that far. And now we lose because we can't go as far. And that happens quite a bit when you talk about patients with frozen shoulder and stuff like that. A lot of times we forget to look at that scapula, where we need to look at that glenouscapular rhythm back there. So here's somebody pulling around in circles, right? They work together, and as they go in a straight line, eventually it's going to cause the little pennant thing here to spin around. And then we're talking about torque here, right? Torque is the ability of force to produce rotational force around an axis. So here we have that line of pull. The center of joint is going to be that kind of that axis, right? And you have the moment arm moving towards the fixed arm, right? So as that moves forward, the perpendicular distance between the muscle line of pull and the center of the joint is what's going to allow that rotational force to occur. At 90 degrees, the muscle has its greatest angular force. So when your elbow is exactly at 90 degrees, you have your greatest amount of force being applied upon it. As it moves towards zero, the stabilizing force has to increase. That's why it gets harder and harder the shorter and shorter that muscle goes. As the movement arm moves closer to straightening or 180 degrees, dislocating force increases, which is why the further you go downward on that eccentric load, the greater chance you have of pulling that elbow apart. And you think of that a lot of times with kids, you know, when they're running through the mall and mom or dad grabs a hold of their wrist to stop them from running, and you'll hear about kids getting nursemaid's elbow. It's because mom or dad grabbed a hold of that elbow and yanked them, and they were already in almost full extension. At that point, the dislocating force is really great. Their bicep hasn't developed yet to develop the resistance force to prevent them from dislocating that elbow, and they can actually dislocate and even twist that elbow and cause all kinds of damage. And then they're off to see an upper extremity specialist. Stability, the center of gravity, is the balance point between an object which torque on all sides is equal. Three planes intersect. Center of gravity for our body, right, is in the pelvis. And it makes sense. If you look at the pelvis kind of looks like our center of gravity, and it's about S2. So if I keep mentioning that the center of gravity, the human body, is in the pelvis, and it falls at about S2, I wonder why I keep mentioning it. I just can't figure out why I keep mentioning it. The center of gravity is somewhere in the pelvis at about S2. I have no idea. I don't know why I keep mentioning it. Base of support. That's the part of the body in constant contact with the ground's surface. I can speak today. Your base of support is typically your feet, unless you're in quadruped, and then the base of support changes. But for most cases, the base of support for us is our feet. The line of gravity, or the vertical gravity line, is a vertical line passing through the center of gravity towards the earth. That's where gravity has its greatest pull. So typically this is going to pass through S2, right at about that center of gravity, right? Go all the way down and should go between our feet. That provides us our greatest base of support and our greatest stability. The closer we move our feet together, right, the narrower we make our base of support, the more our accessory muscles have to work together to keep us in balance. So here's kind of looking at that center of gravity, right? Here's all our planes of access, and that's kind of where all of them intersect. So depending upon what we do, we may have to adjust our base of support, right? If we actually move outside, move most of our weight outside of our base of support, we have to adjust our base of support or we will fall over. Right? When wind's blowing you, you tend to take a larger stance in order to keep yourself fighting against that wind. Where if somebody comes up and pushes you, your reaction is not just to stand there and let yourself get pushed, oftentimes to take the step in order to provide yourself with a larger base of support to prevent falling down. So looking at this one here, so our bases of support are right here, right? There's our two bases of support, right? Our center of gravity is probably somewhere around here. Actually, it's probably somewhere around here, now that I see it. Let me get my eraser out here. There we go, erase that one, bye-bye. And then draw. Our line of gravity should fall somewhere between those base support and allow it to not fall over. That was a really perfect drawing, Mr. McKeever. Let me just tell you. This is why I'm a PTA and not an artist. So simple machines. Oh boy, here we go. We talked about these in physics as well. We have our levers, which are rigid and can rotate around a fixed point when force is applied. We have axis, force, and resistance are our main things, right? Our force arm is our force plus our axis. Our resistance arm is our resistance plus our axis. First class lever is the axis is located between the force and the resistance, right? In this case, a lot of times when you think of the typical first class lever, you think of something like a seesaw. And you can adjust where that axis is to reduce the overall amount of force you need in order to lift that book. So in the current examination here that we have with this lever, it's going to require quite a bit of force to lift that book, which is the resistance at the end of that lever. If we were to take and move that axis further out here, That's going to give us a greater distance we can move this part of the lever, which will reduce the amount of force we have to use. So the longer force arm makes it easier to move. The shorter the first arm, harder it is to move. Okay. Here's typical ideas of first-class levers, right? We have our levator scap's a great first-class lever. Even our sternocleidomastoid is a typical first-class lever. Second-class lever, the resistance is in the middle. The axis is at one end and the force is at the other end. This is a power mover, right? Wheelbarrow is a great example of that. The longer the force arm, the easier it is to move the part. The longer the resistance arm, the harder it is to move it, just like before. Second-class levers in the body, a great one is our gastroc, right? The axis is out at the end. The force is actually going up. The resistance amount is gravity. It allows us to do plantar flexion. This lever favors power, but only moves a short distance. So when you think about it, right, we don't lift our heels a huge amount of distance when we're going into plantar flexion. It's not like the same range of motion we have at the elbow, which we're going to get in now. Third-class levers. This is the force in the middle with the resistance and the axis kind of at opposite ends, right? So this one is going to favor distance. It's most common in the human body, right? Biceps are a great example of these third-class levers, right? Under certain conditions, though, any muscle may change from a second-class to a third-class lever depending upon where you put the resistance. In this case, the biceps is third class during contraction concentrically, and then second class when contracting eccentrically. It's actually kind of cool. Pulleys, right? The number of things that the number of times the machine can multiply the force. And here, the more pulleys we have, the more mechanical advantage we provide. In this case, we've got a fixed and a movable pulley, which becomes a compound pulley, which we talked about way back when in physics, right? Pulleys are all over the human body. The most common, again, we have is our gastrocs, our fibularis, pretty much all of our foot and hand muscles have a mess of pulleys. And if you'd ever be interested in getting into hand therapy, you'll get to learn about all the nasty pulley systems throughout the hand. It's way too much data, for me at least. Because there's just so many pulleys that work along with those, the different, oh my God, why am I drawing a blank? Yeah, the different ligaments and tendons that go along with that. Incline plane, right? In incline plane, we're usually going to talk about when we talk about wheelchairs. There's no real true incline plane in the human body, but definitely with wheelchairs, we've got to work with them, right? We talked about with the wheelchair, in order to have the most ideal wheelchair, we want for every 1 inch of rise, we have 1 foot of run. So that means for every 1 inch we go up, we have 1 foot of length. I'm going to say that again. For every 1 inch we go up, we have 1 foot of length. That's extremely important when designing these wheelchair ramps. It's also really important for your boards because they love to ask questions telling you, you have a patient that has 6 inches to enter his home. How long does the ramp have to be minimally to meet ADA standards? Well, if it's 6 inches to get in their home, the ramp has to be a minimum of 6 feet. At 30 feet, which we will talk about this semester as well when we get into the ADA requirements in Rehab 1 with Dr. Sokel, at 30 feet, you have to have a switchback. The ramp can be no more than 30 feet long. At 30 feet, when you have that problem, you end up with the problem where the person actually has to work a lot harder and keep themselves from rolling back down, right? Wait, did I say 30 feet? Yeah, I got to check it out. I think I've got that wrong. I think it's 6 feet. Let me double check there. No, it's 30 feet. Never mind. It is 30 feet. My brain is not working today. So posture. This is going to be one of the first kind of pseudo comps we work on together. Posture is the position of your body parts at any given time. I'm sure right now with you guys watching this, all of you have perfect posture sitting here watching this. I know I do sitting here recording it. With posture, we have static and dynamic posture, or dynamic posture, right? Static is when we're not moving. Dynamic is when we're moving. We have those 4 anterior posterior curves of the spine that serve as shock absorbers through the body. We have the sacral curve, the lumbar curve, the thoracic curve, and the cervical curve. Those all need to be in balance. Those all have forces, right, that are acting on them. And again, the net of all those forces should be 0 newtons if you have a normal postural curve. So lumbar and cervical curves are convex anteriorly, concave posteriorly. The thoracic and sacral are concave anteriorly and convex posteriorly. So our anti-gravity muscles, a lot of them occur in our core, right? We have our trunk flexors or trunk extensors. We also have our knee and hip extensors and flexors. All of those help keep us upright. Our neck extensors and our neck flexors keep us all positively upright. Those are our primary anti-gravity muscles, meaning those are the muscles that fight for us to keep us upright at all times. If we don't have them, we'd end up on all fours. Postural sway. When we talk about postural sway, we're talking about the sway between dorsiflexion and plantar flexion. A lot of times you'll see this if you watch any of the police shows when they are doing some form of a sobriety test, right? They'll tell a person to put their feet together, and as soon as they put their feet together, they're rocking forward and back and forward and back. Well, it's because they have an imbalance between those postural muscles that are anti-gravity muscles, and that causes postural sway. In the process, they're going to try to correct with their plantar flexors and dorsiflexors, but they may not be as strong as the muscles that are actually overcoming them, so they end up with that nice swing back and forth. So standing posture. When we look at standing posture laterally, so looking at the person from the side, if we put a plumb line, a plumb line is nothing more than a line that will pass through points of the body so we can actually see. You can almost think of the vertical gravity line as a plumb line. That plumb line should pass in the head through the external auditory meatus, right through the middle of that ear. The shoulder should pass through the tip of the acromion. Thoracic spine should be just anterior to thoracic vertebral bodies. Lumbar spine should pass through the lumbar vertebral bodies. At the pelvis, it should pass through kind of at the level point. The hips, it'll go through the greater trach. The knees, it'll fall just posterior to the patella. And the ankles, it'll fall just anterior to the lateral malleolus. So it'll fall just in front of that ridge on that lateral malleolus. What we do to kind of assess posture is we're going to hang a single kind of plumb line or single line from the ceiling and have the patient stand at the specific point that we can kind of measure. So we measure right off that auditory meatus. So we line the line up with the external auditory meatus and go from there and see where that plumb line falls. And that'll tell us how their posture goes. And we'll look at some of those pictures coming up when we do that kind of comp. The ASIS and the pubis symphysis should be in the same vertical plane, meaning if we take and we feel for those ASIS and the pubis symphysis, they should sort of be in line with each other. There shouldn't be too much anterior tilt or too much posterior tilt. If you look at that plumb line from the front, right, the head should be extended and level. The shoulder should be level and not elevated. It should be centered in the midline of the sternum. The hip should come in the ASIS in the same plane. Legs slightly apart, knees level. Valgus, varus, and recurvatum are terms we're going to talk about throughout this whole class. We'll look at the ankle arch, pes planus, pes cavus, and then feet slightly toe out is how we'll end up, right? But as you look at this, it should pass right through the midline of the body. The iliac crest, meaning both ASISs, should be level when we're looking at posture. We don't want any rotation occurring at those ASISs. So this is where we get into a little bit more complex topics, and we will talk about this when we get down to talking about the spine and measurements of the spine, right? But with pelvic tilt, when the hip flexors are kind of shortened down, they are going, so whenever you look at the pelvis, right, I like to think of this as a diamond. Boom, boom, boom. I can draw a diamond, honest, I promise, right? So back here, we have our erector spinae group, and we have our hamstrings. We also have our glutes. Hey, that's cursive, folks. Up here, we have our iliopsoas, and we have our quads. And here we have our trunk flexors, right? Primarily rectus abdominis and the other ab muscles. Where I'm going with this is when one of these, if this is a shortened muscle here, this muscle will be shortened with it. This will be lengthened. This will be lengthened. So your shortened muscle will always be diagonal from it. So if my quads are shortened, my erector spinae are going to be shortened. In that case, my rectus abdominis is going to be lengthened, and then my glutes are going to be lengthened. That will move us into specific tilts. And again, we'll hit that harder when we get into the pelvis. But so if our back extensors are shortened, if our back extensors pull up and our hip flexors pull down, the anterior tilt, meaning the ASIS, is going to go downward. To go into posterior tilt, that anterior superior iliac spine, the ASIS, is going to tilt upwards, right? I look at this as headlights. So if your ASIS is a headlight, right, pointing straight forward, when the headlights point down, right, you're in anterior tilt. When the headlights point up, you're in posterior tilt. The headlight theory has always worked for me. Maybe it's because I think of cars, but whatever you think of, that works for you. Just use it. So when we look at, again, looking at this posture, here's what it looks like standing posture from the posterior side. Everything's nice and level. The PSIS are in the same plane, and the feet are slightly apart, so that palm line should pass through it. Sitting posture. Oh, this is the worst idea for us, especially sitting in that forward slump posture. When we're in sitting posture, we do want to maintain our vertebral curves as much as possible. We want to keep our feet flat on the floor and have some low back support in order to increase that lumbar lordotic curve and make sure our body's in upper alignment. If you look, just that slight amount of curvature in our upper spine drastically increases the pressure coming down on our intervertebral discs. It goes from a 12 pounds of force 3 times up to 36 pounds of force. Supine posture is often considered a resting posture. It has the least amount of disc pressure that occurs at it. A horizontal plumb line will run through the same landmarks as lateral standing, but a good supportive surface is important. Again, when we rest, our discs are allowed to separate out and osmotically absorb fluid. That's why in the morning, you're typically the tallest you'll ever be. Sideline posture is kind of the next best. The bottom leg's extended, top leg is flexed. Pillow between the legs helps maintain that alignment. We kind of lay like this. A lot of times we're gonna have to put our stroke patients in this position, right? In order to get that arm up here where we can actually get it in their view sight. Prone posture, not recommended for stress in the neck because we kind of go way back in the stressing, right? Pillows increase pressure on the neck. There's all kinds of problems that occur here, and most times, unfortunately, in our society, that most patients can't lay prone because they usually have that belly that kind of prevents them from laying prone, especially pregnant when we don't want them laying prone. So here's kind of looking at posture on the disc, or pressure on the disc in different postures. So supine, we only have about 25 pounds of pressure. Side lying, 75. Standing up, 100. Standing up but kind of leaning forward, we have 150. Now we're starting to pick up a load. We can get up to 220. Sitting is 140 pounds of pressure. And then sitting with kind of that forward slump posture or any type of load is going to further increase our disc pressure, right? But when you think about your posture in class. How do you sit? Most people, when you look at them, are sitting kind of in that forward slump posture, that what I call the texting posture, where you have your phone in front of you and your shoulders kind of rolled forward. That's going to overall increase those. I mean, look at the difference. Just standing up, you're at 100 pounds, right? Versus 185. Even if you're standing with that same forward slump posture, you're down by 35 pounds just by standing up. You would think that standing would actually be worse for us, but all the sitting we do is worse. There's all kinds of things looking at now. What's our posture going to look like after we come out of this quarantine and everything, with everyone doing everything via Zoom and sitting in front of a computer all day? So good news. That finishes this lecture. Yay. I know you're all happy. So if you have any questions, please contact me. You've got my email address. I will see you first thing Tuesday morning. I apologize about this, but hopefully this finishes out this lecture. We'll start off Tuesday morning at 8:30 with their X1 and finish our lecture from that. This is me signing out. Have a great day.